Vice Mayor, council members, thank you for your attendance tonight, and community, thank you for the good show this evening, and Happy New Year's to everybody, and hope you had a great holidays. So tonight, council level, to talk about the alternative approach of addressing our flooding in Zone 1. We've had many ad hoc committee meetings, as you've probably seen. They've been very successful, and it's led us to this point where tonight we've asked GIT and his team to put together a couple things that I'll talk about in a few minutes. But to get here, we kicked off this project on October 22nd. So we're now almost 2 months into this, almost 2.5 months into this. We had an ad hoc committee meeting on December 15th, where Giorgio and his team had an opportunity to present to the committee, receive some guidance, and then 2 days ago, he met with us at the staff level to get ready for tonight. What he's presenting to us this evening, don't be looking for a solution tonight, please. So what we're going to see is just the initial analysis of our current system. You know, what works, what doesn't work, an understanding of the flooding, but most importantly, and I think this is as important, I think the council is fully aware of it, but also for the community, is we have changed the level of service and also the design criteria. And if you don't know those words yet, and most of you have because you've been here for 4 or 5 years understanding, but Giorgio will go over that in detail. He'll go through his modeling approach and tell us how he got to the numbers he got to, and then also begin to identify some potential solutions to what might solve the problem. Not necessarily designs or concept, but ideas that might get there. So, looks like the mayor just showed up. I'm going to turn it over to him if he wants to make some comments first. Then sir, we'll kick off, and we've got a mandate to be done before the game starts.
Happy New Year. Let's go.
So, we ready? And any questions or comments from council before we ask GIT to kick off?
We'll see the presentation, I think.
Yeah, I think we will. And so just to kind of put this all in context, so our intent is, this is a workshop today. We've got another workshop, I believe it's in mid-February, and then we have a final workshop in mid-April, and that point is when he will come forward with the recommendations, the physical recommendations on how he wants to move forward. So with that, Giorgio.
Okay, thank you, Steve, and good evening, Mayor, council members, and residents. I appreciate the opportunity to present to you our recent work in terms of resolving the flood issues that are occurring within the village. And as you are aware, there are lots of flooding issues are caused by deficiency of the system. Maybe rehabilitation will be needed, and also additional capacity for discharges are needed to resolve the frequent flooding around the school and around other areas. So this presentation is, the emphasis of this presentation is Zone 1, which is approximately 93 acres. With this, I will go to the next slide. Which one is this one? Okay, so the presentation tonight will discuss the project status, where are we in the projects and what we need to do additionally, where we developed analysis of the existing system, and we will discuss the approach for that. We will discuss the design criteria and how this will affect the flooding. And we'll provide model results and finding, and we will also go over the feasibility of future systems and the timeline for the next steps. In terms of project status update, we already provided the initial report, which covers task 1 and task 2. This report covers the flood extent, the depths, and the duration of the flooding. For this, we developed a very detailed hydrologic and hydraulic model, also groundwater model, and it covers the entire island. Even though we are analyzing, we're providing analysis only for Zone 1, which is 93 acres. We have, the model covers the entire island, and we'll mention why this model, numerical model, covers the entire island. In terms, we're in progress of determining task 3, pump network design. That's in progress. We're proposing slightly different approach, which will address more localized flooding rather than having one single solution for the zone. This is a different approach, and we have reasons to propose this. At the end, we will be comparing the costs of this, and that this will be provided to the council members and to you to make a decision what would be the most efficient. Based on the approach that we are proposing is based on the preliminary analysis that we conducted, that we can provide some savings if we provide a drainage system that includes injection wells at locations where flooding occurs. So this will be resolved locally instead of relying on gravity drainage to the pumps to a pump station that's close to the outfalls. With this, I'm going to the next slide. We are, as the manager mentioned, we started in October. We have been two and a half months in development. We had preliminary information. Our team has worked before, so this gave us a head start. And here I also wanted to mention that the information and the support that we received from the village team, Steve, Rowan, Chris, and also from the Black Village team, Michael and his team, that has been critical to accelerate the schedule. We have reused all of the information that was developed by AECOM, so we had a really good head start in terms of providing this analysis. As the village manager mentioned, we had a meeting with the council members, with the ad hoc committee on December 15, where we provided the initial ideas. So this presentation is based on that meeting, and also includes some additional work that we have done meanwhile since December 15 to now, that looks into the groundwater impacts if we're to inject in the ground, because this will require permitting from FDEP and also from the county. So that definitely needs to be addressed, and I think that's a critical aspect because that provides the feasibility of the project. If the amount of the water that it can inject in the ground and reduce the amount of the water that we need to convey to the outfalls. Just to give you an idea of the extent of the model, the coverage is approximately 1,000 acres, and you can see the nodes, all the nodes and pipes and catch basin and manholes that were implemented. So it is complete replica of the existing system as far as we have the information that's provided to us. We use the most recent surveys by KCI, previous surveys that were done by other teams, and the existing database of the village, in the existing GIS database. And this includes the size of the pipes, the inverts of the catch basins, the manholes, and we have approximately 1,500 nodes representing each of these nodes, and we have 1,500 pipe sections representing the pipe. One of the reasons we consider this to be needed is the topography of the village. Even though we call it flat, but when it comes to flooding, it is not really flat. There is local depressions. There is also the catch basins have limited influence, and that required, we went through a decision that we need to make a detailed representation of the system. If we want to analyze the deficiencies, and we also want to propose upgrades to the system, we needed to have this level of detail so we can basically, currently we have in the model, we can go to a catch basin and we can show the figure, the hydrographs of what is entering the catch basin. Some of the catch basins that have very little inflow, some of them take more. So we have this detailed data, which of course will help us for the final decisions, and especially when we go to the design, we will be able to provide a good direction. If we're doing upgrades with pipes, of the pipes, we can say that's recommended pipe size. Also, the catch basins should be placed in specific locations in order to increase the efficiency. And a little bit about Zone 1, which is right here. This is the outline of Zone 1. The blue line represents the entire model. You can see in the blue line that it extends to the coastal area. And this is needed in order to be able to reflect the tidal impacts of on the system. All of the outfalls are connected to the tidal, but not only that, but also the groundwater is influenced particularly strongly by the tidal. The groundwater fluctuates with the same time as with the tides. And one of the aspects of this is that this changes the amount of the subsurface storage periodically, every 23 hours or so. And it also when it changes the amount of the storage, it also changes the direction of the flow towards the center of the island outside, or outside. Within Zone 1, we have identified 73 manholes and 170 catch basins. They were included in the analysis. And here are the tidal conditions as this is from simulation. The simulation is based on a detailed groundwater model, which is integrated actually with the flow system. So that's one of the differences. The groundwater model goes through the entire superficial aquifer, approximately 150 feet below the surface. And considering that the injection wells that we would be proposing, they're not deep injection wells in the Florida aquifer, they're injection wells in the Biscayne aquifer, in the superficial aquifer more accurately. They are discretized, the superficial aquifer is discretized into 5 layers, and the injection wells are at the 5th layer. So when the stormwater is injected, this goes to the 5th layer, and that is accepted in many locations, and it actually is injected into the saline zone where there is more than 10,000 ppm salinity, and so this is accepted by FDEP and by regulators. And as you can see on this image, I wanted to show you, I don't know if this works. How it works? Yeah, where is it? It's on the side. Yeah. So the upper right image shows when you have a higher tidal water levels, and this occurs twice. You have inflow. The arrows show how the island.
Shouldn't have done that.
Back. Okay, so we'll use. Oh,
There it is.
oh, okay, perfect. Thank you. So the red image shows how the influx comes to the center of the island. The lower image shows during tidal recess, the groundwater flows through. So there is a constant moving, and that's also one of the aspects is we needed to check, does it help or complicates the injection? And for us, it was very important to include the effect of the groundwater. These lines here that are shown here, they show how the water level, this is a transect through the island. It shows how they go up and down. And the movement is approximately 1 foot in terms of the groundwater. The tidal moves 2 feet, but inside the movement is limited to 1 foot. So that gives you understanding of how these are related. There is the amount of infiltration that occurs in the ground. This is accounted for. And transitions from the surface through the unsaturated zone vertically to the groundwater. This is reflected. We also included the vegetation is included in this, and also evapotranspiration, which in a short term is less efficient for flood management, but on a long term, it's a very critical element, the vegetation, because this is one of the most efficient pumps to take water from the ground and send it in the air. So for a long-term sustainability of the island vegetation is very critical. The roots are taking the water from the ground and expelled into the air. And that process is non-stop, continuous. And so all of these aspects are included, and they're integrated together with the catch basins and all the details of the infrastructure. Now we will discuss the design criteria and the level of service. The design criteria, level of service were part of the request, the RFQ, request for qualifications of this work, and they were stated as design year is at 2050. That's the planning horizon, which means approximately 25 years from now. The sea level rise is accounted for to look into no intermediate scenarios. They are set at the coastal area. So what I showed in the picture before, the tidal will be raised by 1 foot, approximately 1 foot, 0.75, and it will be varied according to the NOAA's criteria for no intermediate scenario, and we will provide sensitivity analysis for no low and no high intermediate. So these are critical because they also show the limitations of the system for any of these scenarios. The datum, we use the NAVD 88, the vertical datum. This is consistent with USGS, the Corps of Engineers, and the county. In terms of design storms have 2 components. One is the total volume that falls on the ground. This is frequently, or sometimes it's called depth, rainfall depth, or rainfall volume. It's expressed as inches of the total rain that, for example, if you can imagine the flat surface and you add this water, it will increase by 6.56 inches. So this is obtained from NOAA Atlas 14. It's the source that's being used in Florida. So we're not deviating in any way from the previous analysis. The rainfall depth is 656 for the 5-year. We are providing sensitivity analysis for 10, 25, and 100 year. 100 year is the typical FEMA scenario. These are important to understand the impacts on the freeboard, on the BFE. In terms of the level of service, going back specifically to the 5-year storm, the aspects that we were analyzing is the road weight ponding. The criteria was to have maximum 14 inches within 4 hours, within less than 4 hours. That's one of the criteria. Another criteria is the freeboard for structures. And again, we mentioned the road clearance, that 14 inches for emergency vehicles, 8 inches for police vehicles, and 6 inches for passenger cars. The model provides timestamps. We are analyzing and saving data every 5 minutes, so we can monitor the flood duration and the flood depth throughout simulation, numerical simulation, that's based on the actual infrastructure and physical data. In terms of the tidal boundaries, we mentioned that we are using no intermediate. which is at plus 0.75 feet increase of the tidal. Additional sensitivity analysis are applied for 0.6 feet, plus 0.6 feet, and plus 9 feet for high to represent the NOAA high, intermediate high. On the right up top slide, we are providing the historical data. So for you to see that there is some sea level rise increase throughout the time. On the lower right image, we are also providing the curves that have been developed and we downloaded from NOAA. The blue line is our line that we just put in the middle of the points which represent the mean sea level for the year. So each of these 30 years, we have a data point, single data point, and you can see the blue line shows where it goes. It actually pretty much follows the NOAA intermediate low if we assume straight line, but we do not know if it's going to be straight line or exponential. This is only for illustrative purposes. Here was an important question brought by Council Member Vasquez. What is the rainfall curves that we're using? And we are providing comparison between the 5-year design with 6.56 inches, 10-year design 7.93, the Irma existing storm that occurred in 2017 and typically used throughout Florida, South Florida, to do calibration, and also an extreme event that occurred in June 2022. We also know that there is another extreme event that occurred in September, which was detailed in the by the village. There is detailed measurements of depth and extent of the flooding. So we are comparing against that. The extreme event that occurred in June was total of 12.82 inches, which is almost equivalent between 25 and 50 years storm. And I also wanted to mention that you are probably aware that we talk about 1,000-year storm that is supposed to occur once in 1,000 years, but these storms occurred twice, one in Fort Lauderdale a couple of years ago, and one occurred in Homestead, but it was in the parks, so it wasn't really noticed by any way, but they exceeded the 1,000-year storm, which is approximately 27 inches of rain for 3 days. And so we're not designing for that, nobody is designing for that, but we're looking into the performance of the system for these 4 events. And wanted to mention also that there is a noticeable higher intensity for the 5 and 10-year design when we use the synthetic rainfall. The intensity is critical for the flooding. The higher the intensity, the more flooding it occurs because the system is not able to intake all of the water. And the evaluation, our evaluation of system drainage capacity and level of service includes a number of steps. First, we simulate the design events, and these 4 events. We simulate all these 4 events. We determine the time development of the rainfall, of the flooding, of the extent of the flooding, the depth of the flooding, and we download, not really download, but we extract all the hydrographs at the outfalls and at the catch basins, and this results in a few thousand hydrographs, which we're kind of analyzing, and in terms of the flood data, we're storing data every 5 minutes, so we're able to monitor how this develops. And once we compute that, we also determine the flood volumes. For example, at peak depths, during the rainfall, there is a moment where everything is flooded to the maximum. The water distributes along the low spot, and there is certain volume that's in the ground at the peak depth. So we're taking this peak volume, we call it a peak volume, excess volume, and then from this we're calculating what rate we can use theoretically to drain all of the flood through a pumping or through some kind of through a pumping, really. And once we calculate the pumping rate, we do comparisons, and then we also look at the duration of the flooding above the roadway. So there is like a number of steps involved in this. This table represents of the system drainage capacity. So the level of service, what we determined from our analysis is if we take all of the entire volume of water that's above the ground, because when the rainfall starts, it basically continues for 3, 4, 5 hours. There is a rainfall. We're talking about the synthetic rainfall. During this time, water distributes in the lowest spots, minor portion infiltrates. So there is a distribution onto the area. And we determined that for the K1 zone, we have, so this table is important because this provides really what our targeted values are. The K zone has 93.7, zone 1 actually, sorry, 93.72 acres. Total rainfall is 6.56 inches. The rainfall volume is expressed in hydrological units, typical hydrologic units, is 51.23 acre feet. And that's the rainfall volume. What we have measured, simulated actually, the excess volume on the ground is 2170 acre feet. If you want to convert it to cubic feet, you have to multiply by 45,360, and you get nearly 1 million cubic feet are on the ground. In order to remove these 1 million cubic feet under perfect conditions, and I think that's also very critical because if you place a pump to remove this amount for 4 hours, this pump will be needed to be a 65.6 CFS. That's the capacity. So we consider this to be the drainage capacity. If we assume that there is no infiltration, there is absolutely no other distribution anywhere, we will need 154 CFS. But this excludes anything that's occurring within the urban area. And again, there is infiltration, there is redistribution of water, there is a drainage system that drains to different locations, and there is also outfalls. The outfalls for the, we have a slide for outfalls as well.
You made a leap from 65 to 154. Could you explain?
Where is that coming from?
Yes. So the 154, if we take these 51 acre feet, 51 acre feet, or let's say 1 million cubic feet as a simpler, so this is on the ground. And if we say we instantaneously have this reservoir on 1 million, and we want to drain this reservoir, basically to remove it, this water, to transfer it to somewhere, and we start pumping with 150. So this reservoir is impermeable, there is no other exchanges, it's just a reservoir of, let's say, concrete reservoir. Yeah, the bathtub. And we can pump it for 4 hours at 150 and we'll remove the water. However, in urban settings, that's not occurring. We have other interactions. So what we're saying here that we need to pump 42% of the water needs to be pumped because that's what we calculated with the model. Keep in mind that the model has a resolution of 5 feet, so basically we have millions, not millions, but let's say a few 100,000 cells. It's very detailed, and above each cell there is a certain amount of water we're accumulating, and So this, by saying this, we're simplifying this to only to drain the amount of the water that's above the ground, because the rest of the water is not flooding the island. So 60% is either already drained, because you also have to keep in mind that the rainfall does not occur instantaneously. So it occurs over time, over 4 or 5 hours, even though we call it 24 hours, but the rainfall, really the actual portion of the rainfall, occurs over 3 or 4 hours. So it's kind of delayed. During this time, the rainfall falls on the ground and starts spreading and start interacting with the drainage system, because you still have a drainage system. Even though we say it's not efficient, but it still provides some relief. And so, and then when we do this, we're ending up with the 65 that are excess that we need to drain, or this 1 million. And this is also a reference with the, this also is, you can see also how this impacts the 10-year, and also with Irma, how much it was the excess. Again, these are calculated from the model. We do not have the, we do not have the actual numbers, because we just don't have them. But this is a very detailed model that includes all of the parameters are based on the well-known information, whether from the South Florida Water Management District, whether from the county or from the Corps of Engineers. So this model is based on all of these parameters. And I think that that's a number that we can rely on, like that we need to drain 42% out of the entire amount. As you go further with a higher event, the 42% starts decreasing, because of the efficiency of the system. You cannot remove, it has certain capacity limitations, but that's something that we also will provide as a summary. In terms of the peak outfall discharges, now when we do the analysis, we look at the peak hydrographs, how the hydrographs develops at the tidal section, at the tidal point, which is we have 15, a little bit more than 15, even though they're named from 1 through 17, but there are slightly more outfalls. Zone 1 is managed by approximately 6, but we also know that currently these are in the model, but we also know that some of these are not operating as needed. So, and you can still see that the current system through the outfall, even if we assume they operate properly, it will be 15, 16 CFS. So there is a deficiency of 50 CFS if we still can rely on this. This is the actual existing, and I believe we have data that previous management, approximately 4 or 5 CFS at certain outfalls. Again, this is not really very significant to relieve the flooding.
Yeah, it isn't very well stated, but it's important to have those outfalls, understand what condition they're in. Do we know what condition those outfalls are?
We're relying on the survey data that has been.
We're relying on atlases, but we're not relying on field data. I mean, you're basically looking at a 12, I'm not saying, I'm putting words in your mouth, you're telling me if I'm wrong or not. But you're basically looking at a 12-inch pipe RCP in a plan and saying, that pipe, that's what I'm gonna use. But you don't know whether that pipe has root intrusions, or whether there's a, God forbid, I don't know, something inside, I don't know what.
Yeah,
But,
this is.
but that's what I think we need to know. We need to know that, because your design needs to have not just assumptions that are on paper done by an atlas years ago. We need to know. And I ask,
Didn't we just spend some money recently being the last few years, on redoing our outfalls, putting flappers on them, et cetera? Chris, did we do that?
The outfalls received, what you're talking about flappers, the backflow preventers, they were installed about more like 7 or 8 years ago. The outfalls are cleaned, those backflows are removed, and the outfalls are cleaned.
Well, when you, okay, Chris, but when you
Every
say
year. Yes.
there's two questions. We're always answering with the
Yes,
same answer.
yes,
My question is, what is the condition of the outfalls? Not that they're clean. I mean, you could pass a jet of water.
Correct.
And you could have a root right through it.
correct,
And that will kill your whole conveyance capacity of that system.
correct.
So I'm again asking, can we have these systems once and for all, scoped out into a televised what these outfalls are? I shouldn't ask that. You're the one who should really tell. I need to know what this looks like. Is it a pristine reinforced concrete pipe, or is it is it been collapsed because of the weight of a truck?
Yeah, this is a very valid question. So far, what we have done here is theoretical, like it includes the pipe as it is, but that's something so common here to have.
If we would decide to, if we would decide to proceed with this design, we could do that work later. We don't have to do it now. I mean, so
Yeah.
that.
Okay,
yeah.
but do we know? You say we know. I'm sorry, I'm reading the vote.
Chris knows, Chris speaks with the maintenance people all the time. He knows exactly which condition those.
Okay, so but my question would be to the engineer, what is your level of certainty when you do the plans that we can use those existing pipes? You're the one who's putting your
Yeah.
signature and your seal.
And I just wanted to note,
Yeah.
there's a difference between the outfall and the pipe traveling towards the outfall.
Yes.
That's what you're talking about.
Yeah, well,
We're talking
yeah.
about well-working outfalls.
But I'm
What you're saying is we're not clear on how's the pipe?
Exactly, and thank
Is
you
the
for
pipe work-
expanding
Yeah,
that.
thank you.
But I think,
No,
I think
need
council
that because
member,
that's
I
true,
think,
That's true, that's where I'm going.
I think council member, and you look at this, and we're talking a total of 15 CFS, and could we probably say it's working at 100%? Probably not. Is it probably working at 90? I would say it is. So we're only really talking about 1.5 CFS. So
But he's
that,
given-
that has a
he's-
very small impact in the overall
I
calculation.
understand that, of course, but he's bringing it as an added value to the design. Am I wrong?
Bringing that
I think he's just saying that it's there, and we need to take it into consideration.
I think what this shows is a certain state that, for example, once we finish with this analysis, you will have the choice to fix it. We're giving the exact geometry, because if we start with this assumption, we will end up to question all the 1,500 catch basins. Are they working? Are they not? So I think what we provide is a kind of ideal scenario. And if necessary to provide sensitivity, that's something that we can add. But for the design, really needs to be.
But to me, outfalls are precious. See, that's the thing. You look at it from the perspective of hydraulic capacity. I look at it from the perspective that we have nowhere to discharge water, and we have to maintain those pipes working and functional. And there's two ways of looking at an outfall. Can I discharge? Yeah, 15 CFS, that's not going to give you much. That and a couple of $1 won't get you a cup of coffee. But the thing is that we have the outfall and we have the easement. It should be functioning. In order for it to function, then we can later on, if need be, if we need to build on the system, we already have a declared outfall that works.
Correct.
And that's my message. Is
What are you
not
suggesting?
Figure out what they look like and let's see if we can do something with them even better for the design. Increase the capacity.
Yes, I think that's one thing that we would be suggesting.
We're just not there yet. I mean,
Yeah.
No,
don't-
we'll propose at one time or another.
Yeah, we will have to, one of our suggestion was, there is several suggestions that, based on the preliminary analysis we have. One is to revise the outfalls, to increase the capacity, definitely, because these outfalls that are 12 inches, they're probably
Right.
like very small. But this will be related also to the network configuration, because for some areas we expect to have more discharges. And in this case, we are thinking about maybe 24 inches or 30 inches, up to 30 inches.
Precisely. In hindsight, yes, they don't have a lot of capacity, but
Yeah.
for the future, critical to keep. Critical to keep.
Yeah, absolutely
functioning.
critical, yeah.
Critical to understand what they are inside.
Yes.
And that goes really to, what was being said, what Councilmember Sardina said, just really, the idea is we want to make sure that all these pipes that we're looking into, existing pipes, are televised for once and for all.
Also,
Let's
yes,
have them
quick question.
televised.
So you're measuring what they do today. What's the useful life of these outfalls? And what does that O&M look like moving forward? if they're not replaced or upgraded today?
I think the useful life of the outfalls depends where they are located. I've been in projects where after 5 years you have a big plant and punctures the whole thing, crashes, breaks it, and you cannot even televise it anymore. So typically they should be able to last. Our purpose is to have up to 2050. That's the goal, to have everything functioning to 2050. And if they need to be replaced, outfalls are not simple to replace, but they're relatively simpler because they're separate items that they have easement. So even though they're not, it's not trivial, but it's not as replacing stormwater system in the ground already.
George, correct me if I'm wrong, but the measurement is not really significant based on the total amount of water that you have to move based on the injection system. So, I mean, yes, it's 15 CFM, you have to move 65 or 140.
Huge deficit.
Yes, if you have to move 65, and if our initial suggestions at least 35 CFS can be in the ground, that means the remaining 30 have to come through the outfalls. So that means the increase of the capacity is needed. Even though they may provide 15, that's not significant. It will be integrated system with multiple.
I think you might have lost us some numbers there. Go, if you would, because I think your requirement is 65.53, correct?
Yeah, 65, 63.
Okay, and then you just brought a 30 in there. If you could walk us through that one, because I'm doing 65.53 minus 15, was it whatever it is, 1557, which is a net difference of 50.
Yeah, so here is, in this slide, we placed the deficiency based on the level of service, assuming that we have 15 available, is 50, remaining 50. And what we also mentioned that we have done initial analysis of the groundwater injection, feasibility of the groundwater injection, and we mentioned that we can have 35 without raising the groundwater to the level that's not going to be permitted. So these are 35, and out of these 50, this remains another 15. So then I'm adding this to the other 15. So we need the capacity of the outfalls to be at least 30.
But here we have 6 outfalls that you're outlining,
Yes.
right?
Only
But for the Zone 1, we're only able to use 12 and 15, 12 and 15. So that number is even higher, right?
So this number is even higher, but it's still 30. Like the question is what's available, and
12 and
these
14, correct.
Yeah. And they need to be upgraded, the outfalls. So that's one of the points.
So the message is, and now I want to get to a point because I understand you have a long presentation here. The message, I guess, from my perspective would be retain outfalls at all times in their best conditions. They are precious to us because we don't have access. They can always be expanded if need be, not for this design, but for the future, and understand what their capacity are, really, for real. Stop, please, using atlases to determine it, because we could maximize the utilization. That's a few $1 million that we could save, right? So it doesn't cost that much. What is it, 120,000 to figure out area 1? Let's do that. Let's, not just area 1, let's do the outfalls, let's figure it out.
Yeah, this is one of the most important features that you have the outfalls.
Yes, of course.
Because that's a clear discharge.
That's an
I would
easement.
say even more
That's a-
important is we have the easement.
Yeah, the easement.
And
Yeah.
the easement.
The easement is even more so, because again,
Well-
it's not that, relatively speaking, upgrading an outfall
Yeah, it's not-
is a low-cost approach.
Be surprised, arguments people make, that was a dead outfall, I was able to build on top of that, nobody's using it. I know, we could always take the property, but.
George, a real stupid question. If we did nothing, as of today, with the existing manholes and drainage systems we have, and the existing outfalls we have, without the pressurized injection wells, without pressurizing outfalls, what level of service, in other words, how many more inches of rain can we have to reach this 14-inch level of service that we're talking about? In other words, we're talking about Irma, we're talking about the 5-inch, the 5-year, the 10-year. What percentage of that can we have by doing nothing? In other words, but functions today. This is the marginal thing which will take us from that point to this design criteria. Do you have any idea, or can you calculate that and come back to the next meeting with that?
Yeah, we can review
Because
that.
that would be very interesting, because really what we're paying for in a system is the marginal difference between what we have today and what the level of service we want tomorrow. And so it'll be and then the next thing, which might be a little bit more complicated, but probably not, since you have all the data, what percentage of the time will we go above what we have to today to these various levels of the 5-year, 10-year thing? In other words, is this going to happen 5% of the time, 10%, et cetera? But I think that would be very good when you're making a financial decision. You want to know what you're buying, and that gives you an idea of what you're buying. Thank you.
Yeah, that's a very good point. And actually, there is we're considering we will have a multi-phase approach. We will look into a sequence of steps. One of them will be the first step. What we will do is we will analyze the network. Can we reconfigure the network? In other words, to terminate all the dead ends, to reconnect them, because having a distributed network is very important. It's equivalent to have a lots of urban area with a lots of streets with dead end, and you just don't have any conveyance. If all of the, so we will test that hypothesis first. If we have a complete redistribution network to be all the streets to be reconnected, this will definitely increase the conveyance capacity, and we'll see how this. So maybe that's a first step. Second step is to look at the installing drainage wells at selected locations, or maybe they can be phased in some way. So there is some flexibility in terms of how to make the financial decision and how much to do. And I believe in a way, the way we have this detailed model that will allow this to be evaluated. So
You have to do that evaluation, assuming the design horizon, right, 2050?
2050, yes. So the 2050, there is an impact on the outfalls and reducing the drainage capacity. So that's something that we will have to account for. But again, we are providing the analysis for the current condition and also for the future. So we'll be able to see our initial assumptions at 0.75 feet is not going to significantly impact the drainage system. And I will give you an example. When you had the storm Irma, the elevation in the bay were 3.5 feet. But you had less flooding than when you had the high rainfall in September 2022, in May, and also in June 2022. So the outfalls have impacts, but it's not the most critical. I think the most critical is the rainfall, the amount of the rainfall that comes.
The intensity and the amount.
And the intensity and the amount, of course.
What was the rainfall in Fort Lauderdale a couple of years ago?
In the 1,000 years.
27 inches. 27 inches within 3 days.
4 hours, right?
Yeah. Yes, this was really. So with terms of model results, because again we are doing simulations, numerical simulations, detailed. Like I want to emphasize detailed numerical simulations, and we have 4 simulation events, which we are currently focusing on. Even though we have the rest of these, because we also have to look at your future scenarios. One of the importance of this model and this analysis that once you have this, you can improve your CRS rating, because having a watershed model that's very detailed and provide analysis is one of the critical aspects for getting a higher CRS rating. And I'll give you an example. In Miami-Dade County, by having this model, detailed model with detailed analysis, the county went to category 3, which is one of the highest rated in the U.S. The analysis includes the localized flooding and also the effect of well injection on groundwater levels. I think that's very important. These are the 4 events that we are currently focusing on. And the purpose of this, the Hurricane Irma, is to test the tidal surge and the groundwater response. The key driver is the high coastal stage, again 3.54 feet, it's very high. June 2022, we have rainfall-driven flooding entirely from the rainfall. There was a massive flooding based on the large amounts of rainfall volume. The design storm is the level of service design check. This is based on the NOAA's Atlas. And the 2050 sea level rise scenario includes the design storm for 5 years and also the future, to test the future boundary sensitivity in terms of the tidal increases and changes. And we have is it the same slide?
Yeah.
So we'll skip it. Here is the example of of how the tidal were changing. Again, this is even though not the tidal, but the groundwater at the school. The groundwater went all the way up to 1 foot. And we have done the preliminary analysis for mounding, and we came up with a number that's 35 CFS. 35 CFS can be injected within this area without potentially increasing the groundwater to the level that it will not be permittable. Now we are scheduling meetings with FDEP and with the county to ensure that that's the feasibility of this, but based on the preliminary results, the analysis of the groundwater, the FDEP allows a groundwater model to be used for the regulatory purposes to show that this will not endanger adjacent water resources or cause any additional flooding. So we are pretty safe with the 0.25 to have several wells, or as we decide, at critical locations, not to do a quick flooding. This is the flooding during we discussed in the past. This is the flooding during the 2022, and these are the direction of the flow. So these directions are very important. We're showing them again because based on these directions, we are also looking at where to place the catch basins, at what location, because the purpose is to intercept the flow, not to allow
Fancy stocks.
flooding. And going to the next slide. The feasibility of the future systems, I think these are important to discuss. We think it's critical for every project that's being done to discuss green infrastructure solutions. Green infrastructure is for very low intensity events. It maintains healthy vegetation. It's able to store water locally. And so these are important. This is important for the sustainability and resiliency of the island because it involves vegetation, it involves water quality. So these are really important. The pressurized groundwater wells, we're considering up to 35 CFS of injection. And we're currently looking into different aspects of that, possibly locations of the wells. And we showed during the first presentation potential wells, but these could be optimized. And we are considering also pump stations with force mains to the outfalls to have up to 30 CFS to be conveyed to the outfalls. And one of the positive aspects is that if we're able to first to use green infrastructure to have some of the flows be treated, then we can use the pressurized groundwater wells to have the first flush and everything to go underground because it's also treated. Then the outfalls discharges can be simplified and you may not need the dissipation structures because of the velocities would be less. And also another important aspect I wanted to mention is if you use, we're not considering larger than 24 to 30 inches pipe system. which will result in cost reduction and also ensure sufficient high velocity for not to have sedimentation within the pipes, this is one of the problems if you have a large gravity drainage pipes. Wanted to mention also the low areas. You can see all the roads are in a very low areas, and these are pretty much flooded during the. This is a challenge for the crown of road conditions. So definitely additional capacity is needed to satisfy the condition less than 14 inches.
Giorgio, if I could interrupt, and what conditions lead to this state right here? What has to happen to get us to that?
So this is only the topography is highlighted where it's less than 3 feet. This is coinciding with the flooded areas and also coincided with the problems for having a level of service for less than 14 inches for less than 3.5 hours. So these are typically get flooded and they stay for long. So this needs to be resolved. This is only topography, which is
which is we know where it floods, but I was just wondering what gets us to this point. So you're just showing topography.
just topography. And for another illustration, I'm showing the topography. So these are really the areas that are critical. And it seems that all areas are critical where you have streets. Now, this brings also a question for possible upgrades of the streets, and the previous plans were considering up to 3.15 inches. I've seen in some different locations. So that's something that we would be able to simulate of the effects of this. The drainage system, if you're upgrading the drainage system, it's probably reasonable at that point to raise some of these lower roads, if you would like, if you're considering that. And we also wanted to mention the need for conveyance system upgrades and rehabilitation, or how do you want to consider it. This shows all the yellow links are, first of all, in many cases they're undersized. There is a legend, it's not barely readable, but these are, in many cases, they're undersized. There are a lot of dead ends, or maybe there is assumption that they will flow only in one direction. But I think as a first test, we need to reconnect these to allow connectivity between, to allow distribution, because in other way, you're giving preference to certain locations, but the gravity may not follow. And this has to be integrated with injection.
Yeah. Are you speaking of a new piping system?
No.
Or is it just connecting and manifolding with the existing system?
Connecting and manifolding.
Okay, more of the reason why we want to know the condition of those pipes.
Yeah. Yes.
Right.
Perhaps. Yeah.
But so it's clear, because when we see a lot of pipe there, and a lot of pipe means a lot of cost. So you're not really showing a perimeter pipe, you're showing connections at discrete locations, so you have a connection all throughout. Is that a fair statement?
That's absolutely correct, yes.
Okay, just wanted to make sure that everybody knew when they saw that it wasn't just a massive pipe to build throughout. You're just connecting, but we want to know what those.
Yeah, in many cases, when they have the video systems inserted, they cannot go through.
Okay, a question, can we take that into consideration for today's meeting is this something to move forward with a study I'd like to see? I'd like to request that from staff.
What are you requesting, Councilman?
I'm requesting that we do a televising of the pipes.
Just go pull the pipes.
Whatever, I want them to dictate the scope and tell us what it is.
I can provide recommendation for something that,
Okay.
so
I
definitely.
want to make that, I don't know if it's a formal motion or if it's a.
I think we actually had an estimate scoped, if I'm not mistaken. The same guy who's doing the cleaning of the existing drainage wells I think he also has made a proposal to scope the pipes, if I'm not mistaken. Have you any idea, Steve, what that is? Chris?
There's a different contractor. He does some televising, but not to the level that you're asking.
Okay.
We'd have to get somebody else,
Okay.
but we could.
So you could give us an estimate, that basically?
Sure.
We
So is
we
this-
understand, we understand the intent, yes.
But do we need a formal motion for that, or?
No, we hear
Do we
you.
need a motion for that, Mr. Mayor?
You guys can't.
Okay, Chris can do it.
Keep
No,
going.
But we can clearly interpret,
Yeah,
yes.
Just need to
just
know
come
what it
back
costs.
at the next.
Giorgio, just to clarify, you're in agreement that you've taken it so far. We can't really know the effectiveness of the system until we take this step at some point. And
Yes.
wouldn't be prudent to decide an alternative, which we're not doing today anyway, until we know how those pipes are functioning, fully functioning.
Yes, because
Because
our,
the first alternative, it gets replaced with new, and even if they are working, let's assume that they're working at a pretty high, 80%. There's still aging involved. So they've arrived at a certain age, and they have a certain life expectancy. So at some point, they need to be replaced, they need to be upgraded, et cetera, et cetera. How do you define that in your calculations? How are you going to be able, how do you take that into account?
so currently we're not taking this into account.
I know.
We're looking at the theoretical
Correct,
conveyance.
modeling, I got it.
So then televising, that will provide you with information. And then you have, actually, there are multiple approaches after you identify that maybe there is leaking, because there may be lots of leakages as well that reduce the efficiency of the
Sure.
system, because if it's broken, if you have the groundwater intruding into it, then conveyance, the overall conveyance for drainage is reduced. And there is a slip lining, you can line them. There is methodologies, instead of replacing it, it slightly reduces the diameter. But
And even if they are performing at even 100%, we scope it, it looks good, everything's great, they still have a life. So they're 5 years, they're 10 years, they're 12 years, and there's a life expectancy.
Know what he's saying? You can also line the pipes, let's say,
I got it, yeah.
and so in other words, let's say the pipe. before
Almost
it's lined.
renewing it.
Are they basically plastic pipes, Chris, most of them?
It's
yeah,
Most
liquid,
of it, but there is a mix out there.
it's a liquid
Are there
membrane
many
that
of them
hardens.
concrete? They put
Yeah,
lines
we're,
inside?
yes.
we're doing a job like that.
Some of
I'm
them.
currently doing a job like that in Fort Lauderdale. Fort Lauderdale, instead of doing upgrades for pipes in some areas, they're looking at slip lining. And, you know, you redo,
Talking about, but Ed had a question, I wanted to hear the answer.
They didn't get answered to it.
No, there's a mix of materials that were used for pipes here.
Yeah.
There is some that are plastic, as you call it, and there are some, especially towards the outfalls, is RCP, reinforced concrete pipes.
Right.
But there's also some aluminum pipe out there.
And this extends
Primarily,
life.
my
Yes.
experience, for what it's worth, the plastic pipes, the aluminum pipes, don't last forever, but close to forever, longer than we do, okay? Well, even though they might tell you a life 20, 30, 40 years.
Who's we?
The reinforced concrete pipes is usually where you have a problem. Is that correct or not?
yeah, that's
So
correct.
basically, just ballpark, what are we talking about RCP versus the other materials, percentage-wise?
As far as life
No,
expectancy.
no.
How much do we have?
Do we have
Oh, how
basically
much do
our
we have?
reinforced concrete pipes, is that 10% of the system, 5%?
Maybe 5%.
So basically,
Yeah.
then the pipes we have are primarily aluminum, I call them plastic for everybody here. It's more fun. It's not exactly plastic, but it's
Right.
plastic type material that lasts pretty much forever. So basically, 95% of the pipes, 99, are pipes that should last much longer than most of us will have. Especially me.
That
Assuming
statement
there's
is
no
pretty close,
major
it's,
degradation of the
but
pipes,
keep
yeah.
in mind that these pipes are all in submerged conditions where they're being
Aluminum rusts a lot.
affected,
though.
affected by the salt
Aluminum does
intrusion.
a lot of rusting.
Yeah, well, it does corrode, it's not pure aluminum, we're not talking pure aluminum, and it does corrode, and you
the
do
plastic
replace
pipes,
aluminum
they corrode
pipes.
also?
They do break down, the plastic breaks down, and you
Over
do,
how many
yes.
years?
I couldn't tell you that,
A long, long
but it'll take a while, but with the conditions they're in,
So
they
more
do
than
break
likely,
down.
our pipe system, as Fernando said, maybe there's a problem with obstructions, but as far as wear and tear, especially, it's not like a water pipe or a sewer pipe that has material flowing through it all the time. These pipes, probably 95% of their lifetime, nothing happens, correct?
No, you still have flow running through them
But very rarely.
on a
every
regular
time you have a
basis,
rain.
on a regular basis.
but let's
You
understand
have water
something.
running through them.
Why are we doing this whole exercise? we're doing this whole exercise because we're assessing a different approach.
Right.
So we have to be exact, just like the other engineering set was, exact in what we know. We can't go on assumptions based on atlases. So really, please understand, this is not just to, this is
Correct.
really because Georgia needs the data and the exact conditions of those pipes to say, well, you may have to replace that, or you may not, you can live with
But
it.
aren't we
you
putting,
know?
No,
the,
and
aren't
we-
we putting the horse before the cart?
Yeah,
a little bit here?
we're clear on that.
Yeah, yeah.
Right now, we're just
Well, I'm just
initially
saying,
doing the modeling,
okay.
and then if we
but
do
if-
decide
I'm
to go in a
just-
direction, then we
But
will
But I'm
have to
saying
get
that
evaluation.
you can't,
Evaluate.
Let me ask you another really dumb question. When you have a water pipe or a sewer pipe, the last thing you want is a leak. You don't want sewage coming out of the pipe. You don't want the fresh water being wasted. But you really care if you have a leak in a storm sewer pipe? Because all the worst comes to worst, that same water we're gonna pump somewhere else is gonna be absorbed by the ground around it, correct? So the fact that you have a leaky storm sewer pipe is completely different than when you have a leaky pressurized or even a gravity-fed sanitary sewer pipe. Is that correct?
Yes, that's good.
So it's not really that big of a deal one way or the other, is it?
It reduces the
I mean,
capacity a little
I don't
bit.
know, I'm just asking a
It
question.
reduces capacity.
It does reduce capacity, but no,
Well,
it's
does
not
it-
as.
Why would it increase the capacity if
Reduce.
the water was going out, saturating the area around it and carrying the water through the pipe?
If,
Most is submerged under the groundwater table.
You understand what I'm saying? In other words,
No, I
it's not a
understand.
big deal. Okay,
these
never
pipes-
mind.
these
Sorry
pipes-
for interrupting.
That's why I said they're likely working in 90%, and I think
Right.
we're okay, but we still need to,
Okay,
before,
yeah,
if
listen,
we
I-
choose to
I
go
would
the
agree with
direction he's
Fernando,
going,
we
then we
should
would
know
have
where
to
we at.
evaluate those pipes, yes.
Down the road, we decide to move that direction.
right.
Yeah.
But
Okay.
you also
Carry on.
said a
Sorry.
moment ago that there's
Interruption.
a limit to how much you can add to the
Oh, dear.
groundwater.
Oh dear.
And at the risk of offending,
Should we let him continue?
DEP.
Yeah.
Yeah, so we have a control over that, we can defend what we'll propose.
I was reacting to the hypothetical of a leak, diffusing stormwater into the groundwater.
Yeah,
I took from your earlier comment that there's a limit to how
yes,
much that can be allowed to happen.
yeah, that's correct, because the groundwater starts increasing. And so, looking into this, I think what one of the scenarios we need to do is to decide how these to be reconnected, because numerically, it's easier than do it in practice and see how this impacts the whole, and do all analysis with some kind of optimized reconnection, increases of diameters, and in order to reduce the amount that we want to inject and to maximize the amount that you want to send to the outflow. I think that would be a logical approach.
Earlier, you mentioned that your percentage apportionment of what needs to be drained as opposed to what's stored underground depends on the efficacy of the piping.
Yes, entirely, depends on that. Because as we saw, the outfalls have a very insignificant compared to the entire amount that you need to drain. And you're really relying on these outfalls, but they do not have this capacity based on our analysis. So we talk about how to optimize, and here is a continuation of this discussion. We are proposing to optimize the existing conveyance first. That means that we will reconnect all of the entire pipe system. We will look at to make sure it gradually increases downstream. In some cases, you have a large pipe and then smaller pipe, and it's kind of bottleneck for the flow. So we'll try to look into that, and in some cases, no changes will be needed. You have the majority already placed in the ground, so I think based on the estimate of this, you need another 30% additional. If you want to see how the impact of the reconnecting everything, and the outfalls should be maximized as well, how much you would discharge. And this again goes through reconfiguring and reconnecting the network. So that's the number one suggestion. The other one is to, once we have the effect of this, to look at the pressurized groundwater injection wells, because they provide a localized solution to treat the water where it falls, and instead of trying to convey it, to send it through conveyance. And it doesn't make it easier because all these catch basins, they're reconnected, so all the connections have to be reconfigured in a way that within this area of influence of the well, we need to make sure the water flows towards the well. So there is quite a bit of efficiencies that needs to be, or optimization that needs to be done. And also the pump stations, they will be having a dual action. We discussed that thanks to the team, they had a very good suggestion in terms of reduction of the maintenance, reduction of improving the reliability, reducing the risks of these. So if we have a pump station, and we can pump also to the outfalls. Pumping to the outfalls is beneficial in the aspect that you'll be using smaller pipes, smaller conveyance. So that's number one. You have a proper velocity in the pipes, and it's controllable. And so that's these are the steps that we're proposing.
So from what I hear you saying, Giorgio, is this is not all at once. This is a gradual progression over time, and we're not there yet. And you know, this is the next meeting, but I'm kind of setting the conditions for that. You would be able to estimate where we are in terms of requirement, and then fulfilling that requirement, and what level of service we can meet as we go through each one of these steps. I assume.
Yes, that's
Okay.
correct. True. So we will be. We actually, that's what we're doing right now. We're after we developed the model, we have been doing lots of different simulations, and because this is activity that requires some time, and also reviewing the data adjustments throughout the process to make sure everything is correct. So the next thing is to have these completed. We're doing this as a matter of fact, as we discussed today. We're not ready with it, but we're connecting the system. We're adding artificial links with certain diameters, and we're looking how to perform. So we may be changing the diameter. So there's a number of things that are, we call it optimization. And so once we're done, we will have more clear understanding, hopefully for our next meeting. Meanwhile, we'll be working with the team to be aware of what and to receive feedback of how things look, and is it in the proper way, or is it underperforming, or just to get to the optimized solution that we can propose after testing all different scenarios. So that's the purpose, is to have this done for the next meeting, which is on the 18th, February 18th.
In your December report, you know with this now, you used a number, I think, of 85% impervious area. Now, is that considering the area of the drainage system, 85%, or the total acreage for Zone 1?
The total acreage for Zone 1.
85%, okay, so basically because the streets and swales impervious, that's why it was so high. The other number which I saw in there, if I remember correctly, I think you said that the water infiltrates the soil at 0.05 inches. And I assume that's 0.05 inches per hour?
It's the total storage capacity, how much it,
That's the total storage capacity?
yeah, it went in the ground. Now, so,
Was it on a per hourly basis?
no, it's not per hour. This was a water budget, a final,
Was that 5/100 of an inch?
no,
0.05.
0.5 feet.
Oh, by feet, okay, great,
Yeah.
thank you.
We're doing
No, fine, okay,
we're measuring
Understand.
everything in feet.
okay, that was my questions.
So this has several aspects, especially the exchanges. The stormwater system, it reacts in a matter of seconds and minutes. The rest of the hydrological component, the groundwater, is slower, but it continues for the entire simulation event, for the entire event, and acts for the entire time. Evapotranspiration acts for the, so they have different time scale. And the flooding is mostly affected by the rainfall, these things that occur very fast, rainfall, and then how much is drained to the outfall. So that's to the largest extent the flooding, how it's,
And then finally, if I understand the system, basically we're using, for lack of a better word, the existing system with the existing wells, existing outfalls, existing catch basins, et cetera. And then at a certain point in time, when the wet wells, I guess, and the drainage wells would fill up, that's when those pumps would cut in. And then at what point would the new pumps, pressurized pumps for the outfalls, cut in? Would that all be sequenced depending on the amount of rain that falls?
yes, that will be sequenced actually on, we're currently having a solution that has sensors. We implement sensors. For example, if it reaches to a certain point, we activate the pumping. And also, we did this groundwater analysis to understand what kind of pressure we can add. So when we start adding more than certain amount of water injected, and if there is still excess in the well, this is redirected to the outfalls. So
Thank you.
that would be the system. And I think we need to look into integrate a system that's all automated in terms of how the pumps, when they turn on and off, and it has to be all interconnected.
Yes.
So that you know when this will flow through the outfall, so it cannot be human managed by, has to be automated. And there are solutions and there are examples for that, so that's not new.
Thank you.
At the beginning of this discourse, did I hear you say that 6 inches of water is assumed to be absorbed into the ground?
Not really 6 inches. We have to look at the entire period because it probably 6 inches, but exactly during the flood event is 0.5 foot. Yeah, 6 inches is absorbed in the ground, but this is on a long term, not during the flood. I have to look at the exact 6 inches.
Does, like, the standard modeling include an absorption rate, given typical soil conditions?
It's calculated based on whether it's impervious or pervious, and it's also calculated by, there is, during the saturated zone, it's a numerical calculation that's very detailed.
And I think and I don't want to speak for him, but I think where he's going to is that you identified 154 as a requirement, but you said we only have to meet 42% of it, which is the 65.
that's-
So where is the other 58% going? And I think he's asking, I don't want to speak for you, but I think you're asking, is that going into
That's
the
part
soil?
of it.
Is
Yeah,
that
it's-
part
it's
of
a
that
combination.
58%?
It's a combination of multiple factors. Some of this is runoff, some of this is entering the storm system, and some of this is infiltrating. As I mentioned, the fastest response is in the storm system, what enters in the storm system.
And would you be able to identify where all that 58% goes?
Yes, we have actually, I had the slide, I just removed it.
Because I think some of it relies on the state of our current system, right? And I think that goes back to what
That goes back to
Councilmember Vasquez was mentioning about as well, right?
Capacity.
Yeah, so one aspect of this is that when we do this type of analysis, this is typically what we call it water budget. It's done for a period. When we are talking about flooding, this is instantaneous, a snapshot of a system. So they are not really very well related, but we can say before the maximum, that's what entered the ground, before we had the maximum flood, and what after the maximum, the peak flood occurred, that's what happened. So these can be calculated, but they have to be separated into 2 parts. Because again, the flooding, the flood depth and extent is a snapshot of something that happened, and that's it. The budget is continuation, it's like a state. State 1, there is no rainfall. State, end state, there is a rainfall, and number of processes occur.
But Giorgio, you're doing this on a 5x5 grid basis, right?
Yes.
Yeah.
Yeah, we're doing this on a 5x5, and then it's accumulated over the, and it's also extracted for this zone 1. It's extracted separately. So what we provided here was separate extraction.
Let me ask you a question. Having studied our present environment here and having looked at it, and you're coming up with these solutions, is doing nothing an alternative?
What's your question?
Well, you have a beautiful island, and I think part of the level of service, we all require to have a appropriate level of service, which means that we don't want to be flooded,
Okay.
and we want to have everything maintained, so that's a question of the level of service.
So in your professional opinion, looking at our situation, you would say doing nothing is really not an alternative in your professional capacity?
I believe, no, it's not an alternative. It has to be, you have to address the localized flooding, for sure. That's a common problem in Miami. And we know lots of different locations that flood exactly, and nobody's happy about it.
And newer developments, because they're able to put in the right pipes in, they're able to do the right things, don't have flooding, right? I mean, it's older places like this that have these kind of issues.
Yeah, the places like this have more challenges because a different level of service was accepted at some point. Now, different level of service exists for the new developments, and they all require to be raised above the ground. And so there are challenges with maintaining the old system as well. And
But new development street usually require detention sites or retention sites. We don't have the land to do that, and neither do the Mackles.
Yeah.
Take a big chunk of land and say, we're not gonna build houses there, we're gonna retain water.
yeah, in a way you're lucky because otherwise you have a lot of ponds here. Like on the other side of the eastern portion, you have quite a bit of ponds. So I think the stormwater can be managed, even at your older system.
That's a big difference, Joe.
Do you have images of the
detention
injection
sites or
wells? Is there a typical product?
Yeah, that's typical.
Could we get a look at, get a sample?
Yeah, I could send you the information how it looks. It typically goes to almost sometimes 100 feet below the ground, and it has some equipment with it. It has pumps. It will have different chambers and valves. So there is some requirements, and one of the thing is that we are offering we're proposing smaller pumps, which we believe can fit in the right of way.
Do they each have a emergency generator, or is there a single generator?
They typically include that backup generators are recommended. Duplex pumps, triplex pumps are recommended in order to be able to, if one fails, still to have the ability to continue the pumping.
Frank, there's a drawing in the packet, not in that packet, in the packet that was circulated.
So, Mr. Mayor, if there aren't any more
Shows it.
questions
I have a
from
couple
council,
of-
would you like to open up to public comment?
I had a comment.
But I think, public questions, yeah.
Speak,
But I
speak,
think,
speak.
but hold on, but Councilmember Vasquez has a question first.
Yes, thank you. Georgia, it seems to me, it's a question, it's also a statement. It seems to me, after reading the report, in engineering, we have an old saying, there's 1,000 ways to skin a cat. No meanness inferred to little cute kitties, but that's how we say it, right? So, and I think if we had money to skin every possible cat, we would have all these different solutions. But I think one of the things that I think it's important to highlight that at least, and correct me if I'm wrong, here's where my question comes. What I've seen in your report were the big difference, the big chasm, I guess, between what you're proposing and what AECOM proposed is the initial conception of where's the water coming from, right? AECOM appears to have looked at the water that's coming from the sky based on the South Florida Water Management District curve, right? And using that intensity. Hence the reason why we have so much water, right? I guess. It did take into account groundwater, but I think that the first, and correct me if I'm wrong, I think that the first look was at the storm. You, on the other hand, you're looking at different boundaries. You're looking at the groundwater, You've seen it, I've seen it in your model. And you're looking at sea level rise, saying, hey, folks, you're kind of like sending us a warning and saying, hey, it's not so much about the water that's coming from the top, but maybe the water that's coming from the bottom and the water that's coming in from the side. So I think that kind of behooves us to kind of think about it in that way, especially, and this message is more also for other coastal communities, which do a tremendous amount of investment in these drainage systems. And we're all, little by little, as we progress in this subject, we're starting to see the light. It's great to build, but it's also not great to destroy a community's pockets. As engineers, we also have an economic component. So I ask you to please, look at this in detail. I'm cautiously optimistic. I'm more of the other style of just building pipes, but if we have a system that can function and can mitigate the groundwater and the sea level rise, then I think we may have something here that we could even probably talk beyond out there about ways of doing it. I am a little concerned about your permitting, but that's something that we have to talk about more internally.
Yeah,
That's,
we
that's all
will,
I'm gonna say.
thank you, Commissioner Bastis. I think that's an important aspect, especially for the coast and especially for the permitting. I think we will have clarification. We're confident that with this analysis, we'll be able to provide a solution.
Okay,
For the permitting.
you may have something, yeah.
Who's speaking?
Okay, so before,
To understand
be-
something, so,
I,
thank you, George.
let me do one thing before we do, so I just want to make sure I'm clear what the council is interested in, what I heard from you is, so there's a request to do the analysis of the do-nothing solution, so we understand the baseline. That was requested by Councilmember London. He also requested understanding the frequency of storms that cause this significant level of flooding. Am I correct, Mr. London?
Yeah.
Okay. And thirdly, ensure we get a cost estimate on
Yes.
televising our
Our pipes.
current system that he is intending or considering using.
Yeah.
So that we can get a good assessment of what those are. So I hear those as a three. Okay.
It's frequency and intensity?
In test, yes.
Yeah, well, he gave us the intensity. I think he's looking for the frequency.
Any other general questions?
At the end of the survey, the December
Can you
report.
speak up louder, please?
At the end of the December report, you had this thing about converting gravity wells to pump nodes. How many did you envision needing to cover the 100 acres in Zone 1?
Total, we looked at different options. We're still in the process. We focused on the mounding, first on the groundwater change. Initially, in this report, we showed 8. And then by looking at this, we believe we can reduce them to 6. We can remove it. So that's something that
Batteries died.
I think in a way, this will depend on the localized flooding. I think in overall, we believe that 35 CFS is feasible to inject in the ground. So that's the most important. Whether we'll have 6 or 7 or 8 wells, that's something that we can optimize, because this is not only the injection, but also the conditions of the pipes, the proposed connections.
Okay, and one for the manager. How many high water vehicles do we have? Emergency vehicles?
I don't know offhand, but we got quite a few.
The fire chief said you didn't have any, so I'm just curious. Defined as something over 30 inches of weighting
Oh, okay,
capacity.
well, if you're gonna define it over 30, that's a different story, but I'll be happy to get back to you.
Okay, thank you.
Who's saying what?
I just have one question.
Maybe this is a dumb question, because I have missed so many of your meetings, but I hear nothing about cost tonight. Is that,
We're not there yet. We're not there yet.
so what's the plan, to wait for after the other meetings?
Yeah.
Okay, thank you.
Thank you again.
I was just thinking that the council should consider, because we're looking at this as an alternative solution, moving forward, how that would affect new construction and maybe some of the incentives that we would have in the zoning in order to help with the groundwater and the runoff and that kind of thing.
So just for you to know, that's one of the missions, and Brett just walked out, but that we're having the Zork look at. Looking at, BFE, freeboard, site elevation, those sort of things.
One of the things I propose is making sure that the distance between the top of the dirt and the BFE is reduced. So as we raise the BFE, we're also raising the dirt, but you get greater area to absorb the water.
And those two, like you said, Robert, work integrally together. They have to work together.
I have a question. Giorgio, thank you for the presentation. I really like the approach. Can you go back to the slide that has the rain that Fernando asked you to do? I just want to understand the logic. That next one, that one. Okay, on this graph, the worst event was in 2022. If I understand correctly, we have a bathtub, 1 million cubic feet of water, and we start pumping for 3.5 hours. And then we use that as the approach to solve all this problem. When I look the worst graph, that is the light blue graph, 10 inches of precipitation occurs approximately in 24 hours. Why we don't pump for 24 hours instead of 3.5 hours? That will reduce 8 times the size of the pump that you need.
This was, that's a very good question. That's a part of the level of service. Different municipalities have different conditions. In our case, we have the level of service is 14 inches for 3.5 hours. But that doesn't mean that we can, we have to stop. The purpose is to resolve within 3.5 hours to be able to have a passable vehicle. So that's really the level of service. And that's what we have. But that's something that we can look into because if we assume a longer duration, then the pumping needs will decrease, but then the level of service will suffer. So there is this approach.
And the second question, on the report you mentioned about the Richards equation for Mike Shea, right? Richards equation, and I think there is a typo in the report. There is a plus instead of a minus, but you have also a sink element on that. The sink is only for uproot consumption, but if using the injection wells, that sink element will change. How Mike Shea is using, or Mike, the model program that you are using, consider the injection wells on that calculation?
So the injection wells, we're injecting into the deep zone 5. It's fully saturated, so it's not affected. The only thing that would be affected is the unsaturated zone, which is at the surface. And in our case, it varies because the water table is around, it varies between minus 0.5 to 0.5. So at that level, above that, that's where the unsaturated zone. So the injection wells will not be affected, really.
But it will affect the calculation, right? The model needs to consider that in the sink factor.
There will be no sinking for the injection particularly, but for the saturated zone, that I think that's reflected. I haven't looked at the details, but I'd say it's a good question, technical question that I could follow up.
Thank you.
Okay, I think you have questions for Giorgio. You don't mind saying around a couple of other people? Okay, because others want to go watch a football game. Thank you very much for coming out tonight. Appreciate it.
See ya. Yeah.